Welcome to this explainer. If you're watching this right now, there's a pretty good chance it's late. You might have an electrical engineering exam coming up tomorrow, and you're probably staring at a textbook full of equations that, honestly, look less like math and way more like some ancient, undecipherable language. If that's you, do me a favor. Just sit back, drop your shoulders a bit, and take a deep breath. We're going to get through this together. You see, the concepts we're exploring today aren't actually about impossible math. At their core, they're really just about rhythms, dances, and a few incredibly clever shortcuts that engineers invented simply to make their own lives easier. I'm going to guide you through the source material using these slides, and by the end, you'll see exactly what I mean. To ground all this textbook math in reality, let's just start with a simple question. Have you ever wondered what the electricity powering the very device you're using right now actually looks like? We interact with electricity every single day, right? But it's completely invisible to us. When we look at equations on a page, it's so incredibly easy to lose sight of the physical reality they represent. We aren't just solving for X or Y here. We're trying to map out the actual physical movement of energy that lights up our homes and powers our world. Take a look at the top image here. We see direct current, or DC. Think of DC as the power you'd get from a standard battery. Look at that completely flat horizontal line. It represents a constant, unchanging push of energy in one single direction, perfectly still. But below it, we see alternating current, or AC. This is the power coming straight out of your wall socket. Notice how it's definitely not a flat line. It's this cyclic, rhythmic wave that flows up to a positive peak, drops down through zero, and then flows backward to a negative peak. So instead of a constant push, AC power is breathing. It exhales, then inhales over and over again in a perfect rhythm. This specific, smooth shape, that's what we call a sinusoidal waveform, or simply a sine wave. Okay, so now that we know we're dealing with a wave that breathes, let's move to section 1, anatomy of a sine wave. Let's break down that math. Textbooks absolutely love to throw a massive equation at you right out of the gate, which, let's be honest, immediately triggers a fight or flight response. But I promise you, we can break that scary equation down into incredibly simple visual parts. It's really just a description of a shape. Here's the equation you'll see everywhere. I of t equals I sub m times cosine of 2 pi t over capital T. I know, it looks like alphabet soup, but let's demystify it right now. The I of t simply means we're looking at the current at any given second in time. The cosine part? That just tells us the shape is that smooth, rolling hill we saw just a moment ago. Now, I want you to focus on just two pieces, I sub m and capital T. I sub m is simply the amplitude. It's the absolute maximum peak height the wave reaches before it turns around. How tall is the wave? That's I sub m. And capital T? That is the period. It's literally just the exact amount of time it takes for the wave to complete one full cycle, one complete inhale and exhale before it starts the whole thing all over again. That's it. Height and time to repeat. And this brilliantly illustrates our next little piece of the puzzle. If capital T is how long one cycle takes, well then frequency, which is represented by a lowercase f, is just the flip side of that exact same coin. The equation is f equals 1 divided by t. Frequency just answers the question, how many of these full breathing cycles happen in a single second? We measure this in hertz. So if the electricity in your wall is 60 hertz, that simply means the current is doing that full wave-like dance, peaking positive and peaking negative 60 times every single second. It's literally just the speed of the rhythm. Which brings us beautifully to section 2, the dance of phase, and how waves move out of step. Up until now, we've just looked at one single wave floating all by itself. But in real electrical circuits, things are, well, a lot more social. You have a voltage wave pushing and a current wave reacting. And because of the components in the circuit, they don't always move perfectly together. Instead of a math problem, I want you to think of this as a dance. Notice how perfectly this graph illustrates that dance. We have two distinct waves overlapping right here, one for voltage, labeled V, and one for current, labeled I. Notice how they share the exact same rhythm? They have the same frequency, but they are completely out of step with each other. The voltage wave hits its peak, and then a split second later, the current wave hits its peak. They're doing the exact same choreography, but one is starting slightly after the other. This out-of-stepness is what engineers call phase. When you hear the terms leading and lagging, seriously, don't panic. Just picture two runners on a circular track. The runner who crosses the finish line first, or in our case, hits their peak first, is leading. The runner who hits the peak second is lagging. And that little symbol, the angle theta, that's just the physical distance between the two runners. It is the exact measurement of how far out of step they are. So if someone says current lags voltage by 30 degrees, they're just saying the current runner is 30 degrees behind the voltage runner on the track. Very simple, very intuitive. Now, before we get to the really good stuff, the source material offers us a quick, easy math win called the RMS value, or root mean square. The formula is simply V equals the maximum peak voltage divided by the square root of 2. Why do we need this? Well, remember how an AC wave is constantly going up and down, hitting zero twice every cycle? Because it's not a constant flat line like a DC battery, a 10-volt AC peak doesn't pack the same total punch as a 10-volt DC battery. Dividing the peak by the square root of 2 gives us the effective power. It's basically a shortcut to tell us exactly how much DC flatline voltage would do the exact same amount of work as our breathing AC wave. Let's move to section 3, and arguably the climax of this entire explainer, the phasor shortcut. We're going to freeze the wave. I want to shift the narrative right now from understanding complex math to realizing that engineers are actually deeply practical people. Trying to add and subtract wiggly sine waves that are all out of step with each other requires intense calculus and trigonometry. And guess what? Engineers hated doing that. So they literally invented a cheat code to make life easier. That cheat code is the phasor. The absolutely crucial point here is understanding the transition from what we call the time domain to the phasor domain. Up until now, we've been in the time domain. We're watching the waves wiggle up and down as time moves forward from left to right. It's kind of like watching a video of a moving bicycle wheel. It's accurate for sure, but it's really hard to measure while it's moving. The phasor domain hits the pause button. It takes that complex, moving wave and freezes it into a single, stationary geometric shape, a spinning arrow that we've just paused in place. And this visual right here is the proof. Look closely at this diagram. We no longer have a wave stretching all the way across the page. Instead, we just have an arrow originating from the center. This single arrow captures absolutely everything we need to know about the sine wave. The length of the arrow, that's our peak amplitude, our I sub m or V sub m. It literally tells us how tall the wave is. The angle the arrow makes with the horizontal line, marked as theta, that's our phase. That tells us what step of the dance the wave is on. By turning waves into these simple, frozen arrows, we can use basic geometry to add them together instead of doing pages and pages of calculus. Talk about a lifesaver. If you're still feeling a little skeptical, let me share a direct quote from the source material itself that I think is incredibly comforting. The textbook explicitly states, when dealing with addition and subtraction operation on sine waves of the same frequency represented as phasors, the rotation idea can be kept in the background. This is literally your official permission slip from the textbook authors. They are telling you straight up that you don't need to stress about the fact that these waves are actually spinning and moving over time. For the sake of your math, you can just treat them as frozen static lines on a graph. The tool was designed specifically so you can ignore the hardest parts of the reality. Let's move into our final section, a peaceful takeaway. You've got this. So, we've covered the core foundation of AC circuit analysis, but more importantly, I really hope we've stripped away some of that intimidation factor. You don't have to memorize 100 complex rules if you can just visualize the physical reality of what's happening in the wires. Let's gently summarize the 3 core ideas we've covered today to lock in your intuition before you head back to your studying. Number 1, sinusoidal waves are not scary equations. They are just repeating rhythms, inhaling and exhaling. Number 2, phase is not an abstract trigonometric concept. It's just 2 waves doing the same dance, but running slightly out of step on the track. And number 3, phasors aren't advanced calculus. They are literally visual shortcuts engineered to freeze that complex dance into a simple, manageable arrow so you don't have to do the hard math. Look at the screen one last time. Take a deep breath. I know the textbooks make it look tense. I know the pressure of the exam is totally real. But underneath all the Greek letters and subscripts, they are really just repeating lines and frozen arrows. If you can picture the rhythm and you can picture the dance, the math will naturally follow. Close the book for 5 minutes, let your brain rest, and know that you are fully capable of mastering this. But before you go, think about this. If a single phasor arrow can simplify one wave, imagine the shortcuts engineers use to map out the millions of waves powering an entire city grid at once. It's kind of mind-blowing. I'll leave you to ponder that. Thank you so much for joining me for this explainer, and best of luck with your studies.